This is the outline of my talk. The main topic, as Claudia said, is the equation of state for dense matter applied to neutron, the physics of neutron stars. So I'll start by discussing a little bit what are the important ingredients for the equation of state to describe neutron star, and what are the constraints that we deem important nowadays to construct it. Then I'll talk a little bit about modern sources for the equation of state, which are becoming more popular, and then discuss recent improvements or realizations for the structure of the equation of state for neutron stars, discuss one of the models that can be used to construct this kind of equation of state, which is the chiral field model. And if I get to the end of the talk, and please feel free to interrupt me if you want at any time, I can stop, whatever. I'll talk about.
Veronica, I think you accidentally muted yourself.
I did, it happen spontaneously, very weird. Maybe everyone else was getting muted. I'll discuss possible signals for the confinement to quark matter neutron star mergers, and finish with some comparisons between simulations of neutron star mergers and heavy ion collisions. So although the equation of state, the official meaning of the word, is just a thermodynamic relation between different quantities, usually, at least in astrophysics, that means pressure and energy density. It has a much more, it got a much larger meaning recently. For example, people try to provide a full thermodynamic list of variables, and an important ingredient is also the particle composition. For example, these are some new parametrizations of the chiral field model that my student Alex Clevenger recently completed and made it available in the Compose database that I will discuss later. But I just wanted to illustrate how important it is for us astrophysicists, at least, to have also particle population attached to the equation of state. All these are hybrid equations of state, so they have a hadronic component and a quark component. But usually, not always, but often, softening the equation of state is related to new degrees of freedom appearing. So here, number one is just is a strange one, but then number two doesn't have strangeness included. And then, for example, this two here on the top right have a different sort of interaction. This is a vector-iso-vector interaction that I will discuss later, and it changes it can change drastically the population that appears. And of course, whenever you have more hyperons, this causes a softening of the equation of state. Here on the bottom, I have different higher order vector interactions here on the bottom left, and on the bottom right, also allowing for spin 3/2 resonances. So this is just to give you a taste of how this equation of state looks like for astrophysics. Let's go this way. So you also usually provide microscopic information. By that, I mean like gaps that are calculated if in the equation of state that's the case, or effective masses. And also, finally, the stellar properties. So the standard procedure is to use the equation of state in the Thomann-Oppenheimer-Volkov equations, the TOV equations, which are just spherical solutions of Einstein's equations, because of course this is the simplest case. We could do better than that, but that's usually just for specific cases when you have magnetic fields, for example, which break the spherical symmetry, or for stars that rotate incredibly fast. So the equation of state can be 1D, that's the simplest case. We need to have like a cold neutron star that's in weak chemical equilibrium. but it can also have add more dimensions. For example, for heavy ion collision, as far as I know, usually people use one that depends on density and temperature, but it's in isospin symmetric. But you can also do the three-dimensional one, in which you have this third dimension, which is the charge fraction, or isospin fraction, when it's not isospin symmetric, or it's not in chemical equilibrium. Because when it's in chemical equilibrium with the leptons, the charge or isospin fraction is determined self-consistently to achieve that, to get a charge neutrality. So the three-dimensional ones are of course preferred, and you can add more dimensions, strangeness, for example. In neutron stars, usually strangeness is not constrained. So the strange chemical potential is 0 and is determined self-consistently. The amount of strangeness that comes out. So which ingredients do we need to have a physical equation of state for a neutron star? So we have the crust, which is the name we give to the portion that has nuclei, and the core is where the nuclei has been dissolved into bulk hadronic matter. So the pasta is always something fun to discuss because you have all this interesting shapes. You have pretty much as many shapes as you allow your simulation to produce. More complicated and complex simulations like the ones here that I'm showing from Chuck Horowitz's group allow for more complicated shapes, including defects. Like my favorite one is, for example, the parking garage, where you have slabs connected by something that looks like staircase by some spirals. And these are structures that appear naturally when you're a low density. So you have the electromagnetic force in sort of equal footing of the nuclear force, and all these funny shapes appear. Actually, I just realized I used to call this one Swiss cheese. It's described here at antignocchi. And the reason I put a question mark here is not that the pasta is not important and it's not understood by the community that is there. The reason I put a question mark is that inclusion of pasta really depends on your application. This can be very important when you're dealing, for example, with neutrinos, because these will affect how neutrinos interact with matter for example, stellar cooling. But if you're just talking about calculating the mass and radius for a star using pressure and energy density, the pasta is not going to affect in any significant way your equation of state. So, and I would say that the same thing goes for pairing. Although it's extremely important when you're calculating some properties and the same goes for stellar cooling, it's also important for that, depending on how your, not only your nucleons and leptons and hyperons, but also your quarks appear. This affects tremendously the cooling history of the star. But unless you have very large gaps, it does not affect your equation of state. So therefore, the question mark there. I got this picture here from Fridolin Weber's paper, and I think it illustrates nicely how you have structure in your star. And I like in particular this figure because it's more in scale than other figures, because the crust is actually very thin, although it's important for many dynamical process, is less than 10% of your radius. So most of the star is the core, and what people define as the inner core is that we have all your exotic populations. So hyperons, quarks, you have mesons that condense at this kind of temperature, and maybe even three half spin particles. And also, if you're talking about dense and maybe hot matter, it's important to have a quantum relativistic description, because otherwise you can easily get supraluminal behavior. And I'll give you one example. For example, the APR equation of state, which is widely used, if you try to extend that equation of state for high temperatures, for example, to describe merger simulations, you can get to something like have a speed of sound that's 100 times the speed of light. So especially when you go to high temperatures, it's very important to have a quantum relativistic description. Also that reproduces chirosymmetry restoration, because we know that at high energy, the masses of the particles decrease. Can also add the chiral partners if you are within a parity doubling description in which the masses of the particles with positive and negative parity have their masses reduced and similar to each other. I'm not going to discuss these because I remember that Jan Steinheimer gave a very nice talk and explained this in detail. I think was last year. It could have been the year before, but he did give a very complete talk about the topic here. And of course, you can compare to heavy ion collisions, because that's where all the, not all, but a lot of information at finite temperature for dense matter comes from. And I'm going to come back to that in the end of my talk with some actual comparisons. The constraints that we have nowadays are, the list is getting bigger, which is a great thing. We have the standard saturation properties, like for isospin symmetric matter, like saturation itself, binding energy. And then you have the ones that have a much larger error, like the compressibility, effective mass. The potentials for the hyperons are actually very important for us to calibrate our models. Until very recently, we only had the lambda. Very recently, there was some ALICE data for the sigma. And this is very helpful in constraining the models. But of course, neutron star matter is very far from isospin symmetry. So we also use information from the symmetry energy and its derivatives, the saturation, to constrain the models. We can also use a liquid gas critical point for models that extend to finite temperature. And then, of course, observational data. A very important one, the most important one in my opinion, is that your model has to fulfill the 2 solar mass constraint. Until recently, that was just a mass constraint. But if you look here in this compilation that was done by Hang Tan, you can see that now we have a radius attached to a 2 solar mass constraint. The 2 colors here, the gray and the blue, the gray and the green, are from different collaborations analyzing the same data, the Amsterdam and Illinois, Maryland collaboration. And we have many masses, but instead of putting many horizontal lines here, I just put the masses that are associated with radii. So there's one here with lower mass star. These are both from NICER, both of this double region. And then we have recent information from LIGO Virgo about the gravitational wave event 170817, which was translated into a mass radius diagram region, actually 2 here, using different techniques, either universal relation or spectral equation of state. So although the regions are quite big here, they are constraining. And the reason they are constraining is that when 2 solar mass stars start appearing, or similar to that, I think star ready one, there was one that was 1.97, but for sure there are several stars that have masses around 2. People calibrated the equation of state to be very stiff. And what happened at the point in time is that when you have a stiff equation of state, the stars got bigger because, right, you have a lot of pressure to fight gravity and they got bigger. So especially the regions here from LIGO Virgo are very important in constraining the equations of state that cannot have a very large radius. There are also some horizontal lines here for 2 objects that are in the so-called mass gap. They are too massive to be neutron stars, but too light to be black holes. Not that there's a problem in having a black hole, their mass, but they had not been observed before. So these are all referred to as objects here that could or could not be neutron stars. And as I said, a lot of cooling data, but I'm just not talking about that today. And there's also constraints from theory. I'm not going to go into detail in chiral effective field theory because I think Alexia discussed that last week. But this is extremely reliable at low temperature and low densities. So this can provide a guide for equations of state for neutron stars that have to extend to much larger densities. So I show here how we use it to calibrate our equation of state. So the gray region here is the chiral effective field theory results from Hebel et al. And what we did is use different interactions. And this is the omega rho interaction that I was discussing before. And I was just showing here for 3 effective models, what does it do? When you go from full to dotted lines, it gets into much better agreement to the chiral effective field theory results. So this is how using these to calibrate matter at larger densities. I'm not going to discuss lattice QCD results because I'm not an expert and there were many talks here about the topic, but of course this is a very good guide, and that's the guy I used to calibrate the chiral effective, the paramean field model at large temperature myself. And of course, there's perturbative QCD, which Alexia also discussed last week. But I just wanted to show this plot here, which is from a paper from Eduardo Fraga and the two Alexis. And I think this is very illuminating because the most widely used equation of state for quark matter, at least in astrophysics, is the bag model. And this picture, this diagram here very clearly shows how you have to be careful with this using this simple approach because you have PQCD data. This is all for neutron star matter, which is in weak chemical equilibrium and charge neutral. And you can see where the bag model is usually using equations of state, that usually it replaces the hadronic equation of state at 1 GeV is right when it's already outside the region allowed by a PQCD. So this simple analysis show how this is not really physical. I show here some similar plot. I'm just showing in the astrophysical scales, which is usually not normalized and not in log scale, but showing here how for the chiral mean field model, we eventually do become more stiff than the PQCD regime. I show for several temperatures. So the dots here are marking where the CMF equation of state is getting out of the allowed region by PQCD. And you can see that it happens at larger densities. So like 1400 is absolute maximal in other normal conditions for a neutron star to have in their core. So at least we are not out of the region within there. And then I also show for some larger temperatures that can be reached in supernova explosions and neutron star mergers, how the model stays within the region for the relevant regime. And the reason why it gets out of the region later on is because it has vector interactions that do not disappear as the density increase. So then I switched to modern sources for neutron star equations of state. So there, at least that I know of, there are a few repositories for equations of state. But the composed one is the largest one, which right now has hundreds of equations of state for astrophysical purposes. This was created within the CompStar collaboration and was put together by Stefan, Michaela, and Thomas a while ago, when I was a PhD student, that this was created. And it provides multidimensional equations of state at 0 and finite temperature that can be used for simulations. And this kind of repository is useful because if people want to make some sort of comparative analysis, they can get a bunch at once, or they can just use their favorite, or they can use equations that fulfill certain constraints. So the instruction manual, we put in an archive recently to make it more easily accessible. And also for the lazy people, we also made a very quick guide because instruction manual is big. Very short guide for providers that want to offer the equation of state, and for users that want to use any of the equations of state there. This is just a couple of pages each. And I'm going to talk a little bit more about another idea for equation of state repository, but it's not a real repository. It's a place where you can obtain equations of state. And the reason I don't like calling repository is because it's modular unified solver for equations of state. So the reason I don't like to use the word modular is because, first of all, you'll be able to run the equations of state in real time, and connected to that, you'll be able to parameterize the equations of state from a specific model or first principle theory in different ways as you wish. You know, for example, you want to say you want to use the Karamin field model, but I want to use a parameterization that includes these and these and these particles and fulfill these and these and these constraints. You also be able to combine them. That's why the word unified. So you might want an equation of state that combines a crust with a core equation of state, or you might want to use equation of state that has nothing to do with astrophysics, that combines lattice QCD with another model. So we're going to provide many different options that can be patched together as you wish. This is going to be multidimensional, at least temperature, density, isospinor charge, and strangeness, but might be extended to magnetic fields later. And also this equation of state is going to be connected. They'll be offered different ways to connect them in a more steep way or in a very smooth way. So this is under development by physicists and computer scientists, because of course, if you want to run this in real time, and you'll be able to run this in a supercomputer, all download it and run it yourself. It has to be fast. So this is currently under development. And this also includes the users as part of the development, users from different communities, including heavy ion. So if you have ideas of things that you wanted to provide by muses, you can contact Claudia, which is the spokesperson for the collaboration. So here is a sort of a map of who we are. And our list of collaborators has increased substantially from what was here in the original proposal. And now the second part of my talk, I want to just start discussing the physics, properly saying. And I want to start discussing the structure and the equation of state. And as I understand, this was already discussed last week in Alexis' talk. And I actually got this quote from his paper, that if you combine theoretical ab initio calculations and astrophysical observations, and you plot them, you see that it looks like the equation of state has to get stiff here on the left side to fulfill mainly the 2 solar mass requirement for neutron stars. But it has to get soft because you have to connect this to PQCD. This is a log plot, right? But it has to eventually be connected to PQCD and the conformal limit. So it seems that there is some structure in there, and more people of the community are agreeing that there is some sort of structure. So here, how do you obtain this structure? So instead of looking at the equation of state, which is harder to see, I'm going to focus on looking at the speed of sound instead. And this is the speed of sound as a function of density for several models that are used to describe neutron stars. I show here the famous slide equation with nucleons, but then a bunch of them that have different features. So there's the quarkionic approach here, which had the red one, which has structure. There are equation state of hyperons, with hyperons and a steep phase transition to quark matter when it goes down to 0, the speed of sound. We have one called triplets here, in which you have a second first order phase transition induced due to different pairing schemes in quark matter. So it goes down twice. We have mixed phases in which you don't go down all the way, but you have a lower speed of sound in the mixed phase. We have a crossover equation of state with excluded volume, which end up for the navy blue lines here, which end up making them very stiff at large densities. But just to show you that you do get structure very naturally in realistic models. But the problem is it's hard to determine what comes from the hyperons, what comes from the quarks, what comes from different interactions. So together with Nico Yunis and Jackie Noronha Hosler and their groups, we study in a directly parametric prescription in the speed of sound, how to connect the equation of state with mass radius diagram. And the idea is to look at the constraints here in the bottom plot and be able to go back and see what does this mean for the speed of sound. And as you can see here, if we introduce some sort of bump, and bump is really the simplest way you can go from a stiff equation of state to a soft one. How does this reflect in the mass radius diagram? So when you have a stiffening of the equation of state, what happens is your star becomes big. And it becomes big already at low densities, because some of the bumps here happen at low density. You already star puffs up. And that's when you have this behavior that your mass radius diagram goes to the right and you change your slope. And as you can see here, they all fulfill the main constraints. But if these constraints, the constraint regions shrink in the future, we're going to be able to pinpoint exactly where this puffing up of the star, at which mass or which density is happening, and go back here and trace it back to at which density this bump happens in the equation of state. I just like to rephrase what I said before here. This object here, this gray line, sorry, I cannot not highlight it. We are not certain this is a neutron star. So in principle, all lines here fulfill all the astrophysical constraints that we are sure are neutron stars. But still discussing this bump here, what happens if the bump is wider or is more like a spike? Well, this doesn't really change the radius because the puffing up happens when the bump happens. What happened after the bump is not going to change that. But of course, if you have an equation that's stiffer over a larger range of density, you're going to reproduce more massive stars. So as we determine exactly what's the maximum mass of neutron stars, which are ways to determine that, not just from measuring masses, but there are several papers discussing ways to constrain that from different kinds of observations. We are going to pinpoint this more accurately. And this is going to give us information about the width of the bump.
Veronica, we have a question in the chat by Uli. He is asking on slide 18, what is the thermodynamics behind bumps in the speed of sound? He says he's mostly familiar with dips caused by phase transitions. Yeah, so I think it's related. So if you go back and look at this figure here, so for example, if you look at the navy blue lines, they go up and they go down. So the going down, the softening will happen here because of the appearance of the new degrees of freedom. So it doesn't have to be that the bump itself is caused by something. The bump will just be your equation of state with just pure nucleons. And then when the new degrees of freedom appear, they lower they do the right side of the bump. Also, chirosymmetry restoration can cause that.
This
But you
red
do,
one.
is it correct that you do need repulsive interactions to get a speed of sound that larger than 1/3, the speed of sound squared?
You need vector interactions to
Yes, okay.
reproduce.
Okay, and
to
so
reproduce the tensor physics.
you go up because of vector interactions, and then you come down because of some phase transition or other degrees of freedom appearing, and that causes a bump.
Yes.
Thank you.
So there's in particular, I didn't draw that equation of state here, but there's also an interesting paper from Rob Pizarski discussing how the physics of vector interactions and vector mesons can do this. But again, this explains the stiffening. In Higgs' case, they will disappear later, and that's when you get the other side of the bump. So you need something that appears and disappears interaction-wise, or it can get softened by the new degrees of freedom.
Thomas
And you
Schaeffer
also
is
have something like
sorry, Thomas Schaeffer is commenting also 3 body forces could cause that.
Thank you. But understanding what happens after the bump is much more tricky. Here in the bottom figure, we extend the bump to really just become a plateau. So that's the case that in which you have a stiff equation of state, but then nothing else happens later to soften it. And of course, this is not correct if you extend it all the way in density, because it wouldn't reproduce the conformal limit, which is marked here by a horizontal black line. But you could argue that much later on, there will be some other sort of phase transition caused by, for example, some change in your pairing scheme that could induce another phase transition later on. But this is very hard. It's much harder to see what happens after the bump, because the changes here are in the maximum mass and are much smaller. So that's not our first hope. Our first hope is to see, I already showed this plot, is to see exactly where the bump is by constraining the radius of neutron stars. But you might be asking, based on the realistic equations of state that I showed before, what about having more complicated structure? Because it doesn't have to be a bump. If the hyperons appear, for example, sequentially, you get all these tiny bumps instead. And what we saw is that any secondary construction makes very little difference. So if you compare the top and the bottom mass radius diagrams, if you just eyeball it, it's very similar. So the message here is that secondary structures are much harder to see, but we're very hopeful to find out exactly where the bump is. And the reasons we're hopeful, it's not just because of measurements of mass radius, but also from measurements related to gravitational waves that are not directly translated to the radius, but just looking directly at the quantity that is measured or calculated, the primary quantity that is calculated, which is the tidal deformability, because this is one of the quantities that are calculated by, it was calculated by LIGO, Virgo, in the event that I was discussing, the 1708-17. And we found out that this so-called universal relation, but it's not that universal, we found out, of the tidal deformabilities. This is called the symmetric and asymmetric one, the S and the A. And they are different sums or subtraction of the tidal deformability of the two stars that are merging, that are here called number 1 and 2. So most of the equations of state would just lie on this line. But if you have strong bumps that appear here in the speed of sound, what they do is that they are changing significantly the slope in your mass radius. And what we found out is that no matter how your bump goes up or what kind of bump it is, if it happens very early, it does puff the star and switch the direction of the mass radius curve to the right. And if you compare to a bump that happens later, it doesn't. And because this is related to the compactness, that's mass over radius, which is the quantity that is used to calculate the tidal deformabilities, this creates a change here in the slope of this relation. So there's a line here on the right because we're looking at different masses. So it changes the slope of the line, and it changes in a visible way that you can actually, hopefully, in the near future, be measured by LIGO and Virgo. The problem is that there were several mergers, including neutron stars, but the problem is that for these, the tidal deformability was not measured. Only the first one was measured. So in the next runs that are starting soon, I'm going to show you a chronogram later for the future of LIGO and Virgo. We're going to see that in the next runs, the tidal deformability might be measured. It also depends on how far the merger happened from us. But you have enough sensibility to measure these kind of tidal deformability differences that we're talking about. So we have 1 point here really because we had one merger, but we'll be able to construct a line and measure the slope. So this is a way to use astrophysics to find out more about the nuclear physics. And just to make this more physical, we also tested this with realistic equations of state. So you use the Karamin field model and added the interactions. If you don't mind, I'll go back here. We added the interactions I was talking in the beginning of the talk. So these two equations of state were produced with this omega rho interaction that softens the equation of state at low density. These two here were produced with an omega fourth interaction, a higher order vector interaction, which stiffens the equation of state at large density. And we verified that both of these things are doing is that they either softening the equation of state at low density or stiffen at high density is producing exactly this curve that I was talking about, that it bends the mass radius to the right. So both of these interactions lower the slope of this curve here. So you can also identify that in realistic models. And then I don't want to talk too much about a particular model, but the problem is that parametric approaches get complicated if you want to extend them to find a temperature or away from a chemical equilibrium, just because you have too many variables that are harder to fit. So that's where effective models become useful, because they can be applied in any portion of the phase diagram. And I use effective in a very loose way. Effective just means that it's calibrated to work in a certain regime. And I'm going to discuss one chiral model, but of course, the most commonly used chiral model is the NGL or the PNGL version. You also have the linear sigma model. The one that I'm talking about is a non-linearization of the linear sigma model, which is a bit more complicated, but it has the advantage of more freedom in the couplings, because this model allows hadrons to transform equally on the right and left-handed transformations. And we start using the word CMF to describe a version of the model that has baryons, but also has quarks. And this allows you to have all the degrees of freedom together to reproduce not just first order phase transitions, but crossovers. And the motivation for me to work on that came from low density models. So when I saw people doing supernova simulations and producing models for supernova simulations, and in this case, the crust is very important. So people try to use the same model to model the crust and the core, and in order to get to the crust over larger temperatures. So that was the motivation to do this also for the confinement phase transition. Because usually in astrophysics, you get a model for the hadronic phase, a model for the quark phase, and you just switch when the pressure becomes larger. But in this way, you always have the first order there. So this allows us to use, for example, the critical point to calibrate our model and really reproduce the crossover beyond that. So these were the original references for my work. and was fitted to reproduce nuclear astrophysics and lattice QCD data at finite temperature. And we use the model to, in its three-dimensional version, to study merger simulations. We, and when I say we, is me together with the group from Luciano Rezola in Frankfurt, and more specifically Elias Most, which is in US now. Their code is a full general relativity code. And what we found is something that had not been found before, because usually what happens is that when you have the neutron stars merging, you end up with this very hot ring here, which is reminiscent from the two stars that you had merged. So these are snapshots of the merger, like looking from above. And so this ring is common in all simulations. But what we found is if you allow for a first order phase transition to happen at low and intermediate temperatures, when it gets compressed enough in the center of the star, you cross the threshold for the deconfinement. And then because you have the softening from the first order phase transition, it collapses, it gets very dense and very hot. So that's the first time that this hot region was identified in the center of the merger. Which here by the color code, you can see that also has a lot of quarks, because at low temperature or intermediate temperature is the first order phase transition. But of course, we cannot look inside the merger. It would be nice, but we cannot. But what we can measure are the waveforms from the gravitational wave. These mergers that we did were with masses around 2.8 and 2.9 solar masses. So it's approximately the same as the signal that I told you that LIGO and Virgo measured first, which were two stars with around 1.4 solar masses. Not a lot of masses lost in the merger. So this is around the same masses that we're discussing here. If you have lower masses in this model, you do not reproduce a lot of quarks. If you have much higher masses, you produce a black hole too fast. So these are the signals. And everything to the left here is before the merger, just because of the stars are merging and they are interacting and tidally deform each other. But of course, when the merger properly saying happens, the frequency increases and the amplitude of the wave also decrease. So what we found out is the signal is identical until the merger, but afterwards there's this clear difference in which this shaded line here is the frequency. The frequency gets modified, the amplitude gets modified, and the signal becomes much shorter when the quarks take over. And if you're wondering if that's the case or not, well, we don't know, because for that signal that we measure, we did not measure the post-merger part of the signal. Why not? Because it has a much larger frequency and a much smaller amplitude. So this is much harder to measure. So we haven't measured the interesting part of the signal for nuclear physicists, but we are going to do that hopefully soon and be able to determine what's the structure of the right side of these curves. I think I will, maybe I can show the simulation real fast. Can you see my YouTube window?
Yes.
Okay. So what's happening here is that the stars are merging, and then we're showing different quantities. First was the density, now is the quark fraction. And now it's the temperature. So you have the hot ring around the center, but in the very end, you end up with hot matter from the center in the same regime, which was the densest. So the reason I'm showing the YouTube I have to find my talk again. The YouTube is because the link is there, so you can open it from the PDF later if you wish to do so. Sorry to ask again, but can you see my screen?
Yes.
And in the final 10 minutes of my talk, I would like to discuss a more detailed comparison with heavy ion collisions. And this was done with a different version of the Karamin field model, which was better developed to be used in heavy ion collisions. So this version has an excluded volume and also parity doublets. This version was developed by Jan Steinheimer and more recently calibrated by Anton Motornenko. And this is a different version of the Karamin field model, which reproduces a crossover throughout the entire phase diagram. And here I'm showing the simulation that was performed the same code for general relativity and the merger, and for the heavy ion collision was use this Shasta code. And in this figure here, you can see on the left the astrophysical one, and the right the heavy ion collision one, which was a gold-gold collision. In this figure, we're comparing a final merger mass of 2.9, which is the same I showed you before, and a low energy collision of 450 MeV, which, as I understand, is the kind of energy that is used in Hades. And the interesting thing here is these are very, very different systems, because one system is dominated by gravity and the other one is not. But they do produce similar geometries. And also produce similar temperatures and similar entropies for this chosen setup. So you can see here in the different color code that the merger can get quite hot. This merger is not going to get quite hot in the center because there's no first order phase transition. So we're talking here about the ring that I discussed before and comparing those temperatures and entropies with the one from the heavy ion collision. And as I said, although the geometry is very similar, the systems are different, and they're different mainly because of gravity, as it's shown here better in this time evolutions. So in here, y is the time. So going up, you go forward in time. But of course, we have to integrate our other dimensions and only show one dimension here. But of course, as expected, the heavy ion collision on the right just expand freely in vacuum. You have a very neat behavior here with approximately constant entropy per baryon. The green regions here show entropy per baryon contours, while in the merger is much more messy. And it's much more messy because we had still have the reminiscent of the two stars, which are bound by gravity. So you see that you still have these regions here, which are a little bit away from the center. So the middle of the plot is the center. So you have a little bit away from the center to the right or left, depends on what quantity you want to look at. Temperature entropy is the hottest. But although the geometry in this evolution plane is different, you can, again, I'll emphasize that the temperatures and entropies are comparisons, as you can see from the color code. But I think it's more interesting, at least as an astrophysicist, to analyze everything in the phase diagram. And this phase diagram is a little bit different. It's temperature and density. And the color code here is now for where does matter spend most of the time. On the left is for astrophysics. And on the right is for the heavy ion collision. But here we're doing two cases because the idea is to study how the masses change the setup and how the different laboratory energies change the setup. So we chose two masses and we chose two energies. So the masses are masses that can be easily found in mergers that are expected to be measured by LIGO Virgo. And as far as I know, on the right, they are energies that are studied by Hades. So as I said, there are differences, and the differences are all by gravity, because first of all, you had this hot ring of the reminiscent of these two stars. So you have a little bit more hot regions here at low density. Not a lot, but you have some your matter, your system is spending some time here. And a main difference that after you form this hypermassive neutron star, which eventually collapse to a black hole in a few milliseconds, it's very dense in the center. So you get this very clear, cold and dense center here, which is the bottom of the left plots. But then I want to focus now on the similarities. You do have these trajectories here with comparable entropy per baryon. So of course, in the heavy ion collision, you're expected to follow these lines more or less. And for heavy ion collisions, the larger the energy, as expected, you spend more time with the larger entropy here on the bottom plot. But what we found is that for the astrophysical scenario, for the more massive stars, you also spend more time around this line here that has large entropy per baryon. So in this way, you can associate a larger mass with a larger laboratory energy. And the motivation for that is people saying all the time, oh, we are doing astrophysics in the laboratory. But the question is, what kind of astrophysics are you doing in the laboratory? So that's why we're trying to relate which masses are related to each energy. So you can say, you know, if I'm doing this particular simulation, this particular experiment in the lab, this will be associated with this particular merger. Because in the future, we expect to measure many gravitational wave signals from many mergers, and we have information about different masses. So you can now relate these things one to one. But one caveat is that, as I emphasized many times, neutron star matter, including mergers, is a little bit different because it has leptons, and is most importantly it very isospin asymmetric, and it has strangeness. It produces net strangeness. So what is the translation that you have to do to go from astrophysics to the lab or the other way? So this, I'm not going to claim that this is model independent. I'll claim that qualitative is model independent. So this is a calculation of the deconfinement region in 3 dimensions calculated by my student Krishna Arial using the Karamin field model. So one of the axes is charge fraction, which is the amount of charges per baryon. So pure neutron matter, for example, will be 0, and the same amount of neutrons and protons, or up and down, will be 0.5. I just want you to notice that the translation between isospin fraction, if that's the quantity you're used to look at, and charge fraction is not trivial when you have strangeness. So for the Brown curve, this will be trivial, just a 0.5 shift, but this is actually very complicated, especially large temperatures when you produce strangeness, and you do produce a lot of strangeness in a merger for the strange curve here. The other X is also not baryon chemical potential, is a modified one, and this is the one that's the same on both sides of a first order phase transition. And what we notice here is that this difference is not very large. There is a difference, and as I said, the difference does depend on your model. This was our first approach to the problem, but now we are actually trying different interactions to see how this goes. But the difference is not very large in the position of the deconfinement line. This only goes for baryon chemical potential. If you're looking at as a function of strange or charge chemical potential, the difference will be huge, but not exactly in the baryon chemical potential. And I get to my conclusions. So the constraints are really closing in and allowing us to have a much better understanding of dense matter. putting together laboratory experiments and observations, and also theory constraints. In my opinion, repositories are also helping people to test different equations of state in their simulations without having, to talk to someone and make personal requests. So this is speeding up things. And with the advent now of gravitational waves, we can really study neutron star mergers and understand them better. And this is really a perfect environment to create the confinement to quark matter. I don't know if I emphasized this, I don't think I did. Neutron star mergers are not like supernova explosions. Supernova explosions, you create hot dense matter, but it's very isospin symmetric, it's close to it. Neutron star mergers are not. They're more like a cold neutron star. So if you look at this diagram, you can see that for low charge fraction, the phase transition happens earlier. So this there's some difference here. So this is kind of nice for astrophysics. Increase our chances to see it. So neutron star mergers can be compared to heavy ion results. You just have to sort of translate them. And there's a lot that's coming from the astrophysical side. NICER has more data that they're analyzing for more mass radius regions that will be provided soon. But if you look at the calendar here, we're about to start the fourth run of LIGO and Virgo, and now there are more. There's also LIGO India, there's Kagra, there's more interferometers that are being constructed, and they are going to be in sync, so they can all look at the same object at the same time, and try to increase the precision, among other things. And to get to the precision, the 05 was the one that I talked earlier in the talk, that's the one you need to measure tidal deformability, very small error, because they're upgrading the detectors and all that in order to really learn more about dense matter. That's it. Thank you.
Thank you very much, Veronica, for this very nice overview. So I have a couple of questions in the chat. One was asked by Hui Chao Song towards slide 26, 27, but I decided to wait until the end of the talk since you were almost done. She was asking, what is the expansion rate comparing neutron star, and gold-gold collisions?
Sorry, what do you mean by expansion rate? You have to explain it to me.
I'm wondering which system evolve faster or slower?
So
yeah.
Got it. Thank you. So the time frames are very different. I'm not sure this is yes, it's here in the legend. Sorry, it's hard to see. So in mergers, everything happens in a millisecond scale. It depends on the mass. The more massive the faster it happens. But I would say it stays between a few and many milliseconds, a couple and many milliseconds. So it's a very different time frame, the heavy ion collisions, which is shown here in Fermi over C.
So that, Claudia, that relates to my question.
Okay, go ahead then, and then I'll ask.
Yeah. So with that in mind, what if you now go one slide ahead? Yeah. So you highlighted one difference here, which is you highlighted the similarities. You highlighted one difference, which was the cold nuclear matter in the left plots. But you can't tell from a diagram like this whether things are in equilibrium. And in the heavy ion collision with timescales of Fermi over C, they're much less likely to stay in equilibrium than in the neutron star case with timescales of milliseconds. If I can do the counting right, they differ by almost 20 orders of magnitude in timescale. I mean, 19 orders of magnitude. So other than the difference in the mu's, which you highlighted, what are the differences between the two sides that relate to the timescales differing by 19 orders of magnitude? Other than the mu, which is in a sense related, because the reason for the difference in the mu is the difference in the time scale, because there's no time for weak equilibrium on the right, and there is on the left.
I think there are many answers to this question. The first one that pops in my mind is what's shown in this diagram, that you can see that things in a heavy ion collision look much more smooth in the simulation as time goes by than the one in the merger. So there's a lot of dynamics going on in the merger. So when you look at snapshots like this one, it's harder to grasp what's happening. For example, if you make a plot, which I like to make, of the hottest or the densest part of the merger, it pops sort of all over the place because there's a lot that's happening in these milliseconds there. So that's a good point, that what's happening here is much more messy. And I think that's why these time diagrams might be more useful, these time evolution diagrams, because then you can see, of course, you lose information here because they're integrating over the transverse, the equatorial place in the case of the merger. But at least you get some average idea of what's happening. And if you did this in a 3D plot, you'll be even more messy if you had not integrated this out.
It's interesting that you're saying that the one on the left is more messy. In space and time, it's more messy because it can have different characteristics here and there, which are there's kilometers in space and milliseconds in time. But there's another sense in which on the right is more messy, which is that because the evolution is so fast on the right, you can't just say, well, I know the T, I know the mu, so I know the properties. It's equilibrium matter with a given T and the following 3 mu's. That's it. From T, mu, from mu B, mu Q, mu S, and T, I know everything about the matter because it's in equilibrium with those T's and mu's. That's not a good approximation on the right. But it is a good approximation on the left, or is it? Are there any ways in which on the left also you have to worry about non-equilibrium microphysics?
So I'm not sure that that's what you're asking, but we try to block out these pre-equilibrium regions here in the right diagram, where is marked as freeze out, to try to not discuss that part, which didn't really have a physical meaning from our simulation. I don't think there's an equivalent on the left.
With that, this was a great
I mean,
talk.
I think the one thing you can have is, so in the neutron-star merger, strong interactions are always in perfect equilibrium because milliseconds is much longer than anything. But of course, electroweak is not in equilibrium. So in a merger, viscosity comes from electroweak, and in a heavy ion collision, viscosity comes from the strong interaction.
Correct.
So there's a lot of discussion about viscosity these days, if it's important or not for merger. So I don't know if I made that clear, or if you guys already knew by the name of the codes, but these were all ideal hydro simulations. All the viscosity is coming from the shock.
This sets up Thomas's question from the chat.
That's right. I was about to ask Thomas to please ask his question again.
Sorry, I went ahead.
Yeah, so I think you just answered it. So in these simulations, all the entropy is made by shocks because there's no other mechanism. Is that right?
Yes, correct. So there's a lot of research going on from mainly the group from Mark Alford, and also Elias Most and Jordan Oroya, trying to determine how important bulk viscosity is, and trying to introduce that for the first time in this kind of merger codes. So I think soon you'll start seeing a result from this kind of simulation.
Yeah, and there's back of the envelope from a long time ago, back of the envelope estimates that say bulk viscosity might be important because of the weak non-equilibrium that Thomas just said. So we'll see what they find. Do you have to worry about shear viscosity also, or is it only bulk that you have to worry about?
I'm not an expert in any ways, but what I learned from my discussion with these guys is that shear is not relevant, not as nearly relevant as bulk could be.
Okay, I see Bernd raised his hand. Go ahead.
Yeah, so I have a question that actually is related to what was just now discussed about viscosity from electroweak interactions. Do you have to worry at all about neutrinos? I mean, in supernovae, neutrinos and neutrino transport plays a very important role. In neutron star mergers, are neutrinos relevant, and how are they treated if they are?
So that's very interesting question. And as far as I understand, the supernova is community is a few decades ahead, and they developed their neutrino interactions, built them into their codes and in a very nice and physical way. And this is slowly progressing now in the merger community. This simulation that I showed has a very simple, just a neutrino liquid scheme that's very simple. But this is something that a lot of people are working on right now to try to improve this.
Okay, I don't see any raised hands anymore. If anybody has a question, please raise your hands. I had a couple of questions as well. So at the beginning, when you showed all of these phases for the nuclear, for the crust, I was just wondering, how do they come about? What are the conditions for each one of them?
So in the beginning, people had like nuclei, like bubbles and bulk hadronic matter, and it just dissolved. And then when people start including in their equation like more complicated shapes, like what about if you offer the system to form spaghettis or lasagna, which I think were the first ones, what will happen? And they saw that they lower the energy, so they will happen. So you have, it's not what I'm showing here, I should have a more like stratified structure in which you go like, you know, the nuclei start getting bigger in structure. It's kind of what's shown here in a way. So, you know, your gnocchi connects and becomes spaghetti, which connects and become waffle. So you have a clear structure of where you're getting to a point that's, you know, is mainly bulk matter, some holes in which you have the matter of the nuclei. But then later came the actual simulations of not imposing shapes, just letting the system choose the shapes, which are very computational demanding, of course. And then what people found out is that you have more complicated shapes that appear if you allow them. And what they found is that you have this defect, so they're not perfect spaghetti or something. And the defects are actually really important for the cooling properties, for how the neutrinos interact.
Okay, thanks. And then I had a question about this exclusion plot. I think the first one you showed on slide 8, maybe. No, maybe 9. Here it is. So what is this banded 3 solar masses? Can you comment on that?
So this was
maybe you didn't.
This was observed electromagnetically, and it's a companion of a giant star, which is probably, by like, you know, just intuition, it's probably a black hole, but they couldn't determine.
Okay.
So people just, you know, start putting the plots just to see, oh, can we get there if it turns out to be a neutron star? But there's a lot of research going on in this mass gap, which is between 2 and 5. And try really to determine, if you can determine what is the cut, then you'll be able to you know, determine lots of properties much better. But the problem is the cut might not be a cut, right? Because what I spent a lot of time studying magnetars, and if the magnetic field can be really large, we already measured a magnetic field of 10 to the 16 Gauss. So what I found, if you start measuring magnetic field of 17 Gauss, which is perfectly reasonable because it's supposed to increase just by like flux conservation, we see that the mass can be much larger for magnetars if that's the case. And the stars that rotate faster can also have more mass. So it might not and never be a sharp cut, but just a massive region. But probably I would say that one is a black hole.
Thanks. Meanwhile, we have a question by Chiming. Go ahead.
Thank you. I have a question regarding two questions. I know from other people's study using chiral effective interactions, they found that the symmetry energy slope is about 60 MeV or so. Do you get a similar numbers in your analysis of the merger events?
Yes, so there are a few things that are important there. So I think when I started working with neutron stars, we didn't have good measurement for the slope of the symmetry energy, which is really what determines, how, for the people who are not familiar, how stiff your equation of state, how fast your equation of state will get stiff, your neutron star equation of state is density. That was not really a constraint. And then data start coming saying that the symmetry energy slope was very, very low, which is actually really consistent with these results from LIGO and Virgo here, that say that the radius is small, because if around saturation, the equation state is soft, the star will be smaller. And this really constrained everyone's equation of state. But then now recently there were results from PREX too, saying that the symmetry energy slope is large, which
so that has a lot of problem, right? Yeah, we know CREX has a very small neutron skin thickness, and that requires a smaller L. So I think the CBAP people, they have to sort that out. The two measurements are somehow in conflict with each other. The PREX2 and the CREX experiments.
Yes, I would say that the field is very messy right now. I have a paper that had two referees complaining. One said that my symmetry energy was too small, one said it was too big. It's a very funny situation to be in. So it depends on what you're dealing with.
I have another question. In your summary, you mentioned those mergers provide opportunity to pin down the transition from hadronic matter to quark matters. Do you have some information from your analysis studies at what baryon density nucleonic matter make a transition into quark matter? 3 times, 4 times, 5 times? You tried many equations of state. Which one works the best? Give you some information at the critical baryon density at which quark matter appears in neutron star.
Yes, so I think one of the ways to obtain it is from this kind of work, that there are many different papers coming to archive every day, trying to see where this connection here really takes place, which it will be the lower of our bump. But in my opinion, this from mass radius alone, this is very, it's hard to obtain. I didn't show you bumps going all the way to 0. We have that in the paper here. I'm just showing you all the way to the conformal limit. But if there's a first order phase transition to quark matter, this line will go all the way down, and your masses of your star go down. So what gives you the information here of what happens after your bump, like the going down part, is really the maximum mass of your stars. And as you can see here, this is still unknown. We know for sure it's larger than 2. There's one measurement of radius around 2, but it's a wider one. So I don't think that this will be solved too soon, because it probably is not much below 2, but if it's a 3 or 4 or the way that this happens, if it's steep or not, I think it's a little bit farther in time.
Okay, I'll wait. Thank you.
Okay, thank you very much. I don't see any other raised hands. Last chance for anybody to ask questions to our speaker, Veronica. Okay, if not, thanks again very much, Veronica, for this great talk. And so this is the last talk on this series, and we will be back in the fall, hopefully with a new series of seminars. And I would like to give the line back to our chair, Xiaofeng Luo, if he has any comments to make at this point.
Yeah, thank you everyone for joining the last seminar in the 4th series. So I want to thank the great efforts of other 5 organizers, Wooly, Nu, Claudia, Hui Chao, and Yi actually to support this. And also, we organizers would like to express our gratitude to all of you from worldwide and day and night for joining and have wonderful discussion and to make this seminar series very successful. Thank you. And as Claudia said, we are discussing the 5th series. So hopefully we will see you in September. Yeah, thank you.
Thank you.
I'm wondering whether Uli, Nu, and Claudia want to say something.
I would just like to thank you, Xiaofeng, for doing a great job as a chair, coordinating all of the efforts during this 4th series. Thanks a lot.
Thank you.
Yeah, same here. Thank you, Xiaofeng. Thank you, everyone.
Thank you.
See you in September.
See you. Okay.
Bye.
Bye.
Thank you. Bye-bye.